Our third lesson in Unit 7 deals with what are called special right triangles. These special right triangles have certain angle relationships and therefore they have certain side length relationships. This is all rooted in the Pythagorean theorem, understanding the theorems about isosceles triangles, and applying that information from Units 4 and 7 kind of together here as we continue to explore area in polygons. And so here are the two goals for the lesson: to use the properties of 45, 45, 90 triangles and 30, 60, 90 triangles. So 45, 45, 90 simply refers to the angle measures in an isosceles right triangle. So if we have an isosceles right triangle where the lengths of the legs are the same, where they are equal to each other, then we know in this triangle, in this right triangle, that the base angles have to be congruent. And so if this is 90 degrees here, then each of these must be 45 degrees, because 45 plus 45 plus 90 will add up to 180 degrees. So the question is, if I know that the sides have the same length, whatever it is, let's just call it x, then what is going to be the length of the hypotenuse with respect to the length of the leg? Essentially what we do here is we have this Pythagorean theorem relationship, as we've already explored in our previous lesson. And we have, of course, a little bit of computation to do once we substitute in the variables x for the length of the side, or the length of the leg here. Then we find out that we have x squared and x squared make the hypotenuse squared, or 2x squareds. To find out what c is, we would take the square root of our 2x squareds. Well, we know that when we are trying to simplify radicals, one of the things that we attempt to do when we're simplifying square roots in particular is identify a perfect square factor. Now, 2 is not a perfect square, but the square root of x squared can be simplified. So using that product property of radicals, we can rewrite the square root of 2x squared as the square root of x squared times the square root of 2, which means that we get x times the square root of 2 for the length of the hypotenuse. So this means, here's what this means. It means that if we know the length of one of the legs, then we know the lengths of all three sides in a 45, 45, 90 right triangle. Likewise, if we know the length of the hypotenuse, we can divide by the square root of 2 to find the length of the legs in a 45, 45, 90 right triangle. We'll see this on the next slide. Next, we want to deal with this situation where we have an equilateral triangle. An equilateral triangle has angles whose measures are all 60 degrees, all right? And for simplicity's sake, one of the things that I'm going to do is I'm going to call the length of each side, I'm going to call 2x's here in just a little bit. But one thing that I want to do is we're talking about 30, 60, 90 triangles, and we learned in Unit 4 that when we draw in the angle bisector in an isosceles triangle to cut it into 30 degrees and 30 degrees, it is also the perpendicular bisector of the base of that isosceles triangle. And therefore, when we are dealing with a 30, 60, 90 triangle, again, that's the measures of the angles in the triangle, 30 degrees, 60 degrees, and 90 degrees, we can build and understand the angle relationships. I'm sorry, the lengths of the relationships amongst the lengths of the sides based off of the angle measures. And so I'm going to call that side 2x's. That was the length of the sides in this equilateral triangle. But when we cut this part in half, these 2x's got cut into x and x. All right? So now I just need to find the length of this other leg that I'm going to call b. I'm going to use Pythagorean theorem again. We are going to get to do some fancy algebra 1 here. And when we do that, we will be able to find the length of the longer of the two legs. The longer of the two legs. So again, just a real quick hit here. In an isosceles triangle, angles of equal measure are opposite from sides of equal length. In a triangle that's not isosceles, the larger angle is across from the longer side. So the largest angle is 90, the longest side is the hypotenuse. Next we have the 60-degree angle, so the next side is longer than the shorter side, all right? It's shorter than the hypotenuse, but it's going to be longer than the side that's opposite from the 30-degree angle. So in this case, we'll have x squared plus b squared equals c squared. All right, we get to do some fancy Algebra 1 here. And the Algebra 1 that we're doing for the most part is going to focus on Unit 10 of Algebra 1, wherein you are dealing with squaring monomials and doing a bit of subtraction here. We have 4x squareds. We're going to subtract 1x squared. We're down to 3x squareds, but now we need to take our square root on both sides. And again, we're going to have the same situation we had on this step. We're going to take that square root by finding our perfect square factor and leaving the not perfect square factor, which means that I can take the square root of x squared, but I cannot take the square root of 3. So the length of that longer of the two legs, there's two legs, there's a short leg and a long leg, is going to be x times the square root of 3. And so this is our recipe for our 30, 60, 90 triangles. All right, now this is the explanation. You will not need to provide me with the explanation. You need to have that in your notes. I'm not going to have you derive this on an exam. But what I am going to care about is that you know these relationships, all right? That you understand how the lengths of the sides are related to one another in a 45, 45, 90 and a 30, 60, 90 triangle. All right, so those are the recipes. We need to know those. And the derivation there is your fancy Algebra 1. But let's kind of move on and let's understand these concepts and ideas. So the way that we are going to create and solve equations, again, here's the deal, folks. You need to be able to write an equation and then solve the equation, just like we've been doing this entire unit. You're going to continue doing. This is going to set you up for success when you go to Algebra 2. Essentially, write this down, that the hypotenuse in a 45, 45, 90 triangle is equal to the length of one of the legs times the square root of 2. That is our formula, all right? And then we're going to apply that in these exercises. So here we have 45, 90 triangle, 45, 45, 90 triangle, 45, 45, 90 triangle. If we know that we are dealing with an isosceles triangle, then we know that we are dealing with leg lengths that are the same. Now here's the fun fact, folks. You can pretend that we did not learn anything new, and you can just do a squared plus b squared equals c squared, a squared plus b squared equals c squared, a squared plus b squared equals c squared, and solve for the variable. But that's not the point here. The point here is, why do 6 or 7 steps of Algebra 1 Pythagorean theorem when you can do 1 or 2 steps of geometry, all right? So here's what I want to show you. If the hypotenuse is equal to the length of the leg times the square root of 2, then in this case, h is going to equal 9 times the square root of 2. I'm done. I found out what h was. Over here, if the hypotenuse is equal to the length of the leg times the square root of 2, then I can take the hypotenuse is equal to the length of our leg times the square root of 2, and I can do my multiplication here. 2 times the square root of 4, which is 2 times 2, which is 4. On this side, we know that the hypotenuse is equal to the length of the leg times the square root of 2. We're going to write down that formula every single time so that you can build your understanding of that relationship. The length of the hypotenuse is equal to the length of the leg times the square root of 2. Well, this one's going to be a little more challenging, okay? It's the harder of the simplifying with the radicals, where you have to divide both sides by the square root of 2. Sorry for the handwriting there. When we divide by the square root of 2, we need to rationalize our denominator. We're not allowed to leave our radicals in the denominator of our fraction. The way that we approach that is we multiply our fraction by 1, represented as that denominator over itself. That gives us 16 times the square root of 2 in our numerator. The square root of 4, square root of 2 makes the square root of 4 in our denominator. So we end up with 16 times the square root of 2 over 2, which is 8 times the square root of 2. All right? And again, if you find it more compelling to do all of the Pythagorean theorem work, you are welcome to do that. Make sure that you have these examples in your notes. The 30, 60, 90 relationship we've already discussed and described. Went ahead and proved this relationship that the hypotenuse, which again, you need to be able to identify which side is the hypotenuse. That's the one opposite from the largest angle, is the longest side. The two legs are the ones that are perpendicular to each other. And there is a longer leg that is opposite from the 60-degree angle. There is a shorter leg that is opposite from the 30-degree angle. And here are your two formulas. The length of the hypotenuse is equal to the short leg times 2. So if this is x, this is 2x. If this is 10, this is 2 times 10 makes 20. If this is 15, then 2 times 15 makes 30. The length of the longer leg is going to be that short leg times the square root of 3, as we demonstrated in the proof earlier. So have those formulas down. In these 30, 60, 90 triangles, you'll notice that I've reoriented them. And even the drawing that I had in this last slide was rotated and flipped from how we first did our 30, 60, 90 example when we were describing and discussing how to show these side length relationships. All right, so we need to be able to visualize this in these different ways, flipping it, rotating it, changing directions, so that we can understand those relationships. So again, if we know here that the hypotenuse is equal to 2 times the short leg, then we can say that 8 equals 2 times x, or 4 is equal to x. I'm done with that. The length of the long leg is equal to the short leg times the square root of 3. So y is equal to the short leg, which is 4 times the square root of 3. Oh, that's my answer, 4 times the square root of 3. Done. No work to do. If we write our formula, if we understand the relationship, then we can get that answer pretty quickly. Over here, the hypotenuse is equal to 2 times the length of the short leg. So in this case, Q is equal to 2 times 2, or Q equals 4. Done. P is the longer leg. Again, opposite from the larger angle is the longer side. So the longest side is the hypotenuse, the longer leg, the shorter leg. All right? So in this case, the long leg, I'm going to do this over here if that's all right. The long equals the short one times the square root of 3. So P is the length of the long leg is equal to the short leg times the square root of 3. Oops, I'm done. No work to do. I wrote the formula. I plug in the number. I have the answer. There's no thinking, no extra effort. You apply the formula, you plug in the numbers, and you get your answer. Now over here, this one's a little more challenging because we're going to have a situation here where we want to understand that the hypotenuse is equal to the short leg times 2. Well, my short leg is D, and my hypotenuse is F, so I have F equals D times 2, but I don't know what D is. So I can't solve this. I need to figure out the length of the short leg using the length of the long leg first, all right? So we've got a little bit of work to do here. I'm going to find out that the length of the long leg is equal to the short leg times the square root of 3. 12 is equal to D times the square root of 3. Just like the last exercise and the last example, we have to do some division, which means we have a little bit of simplifying of radicals to accomplish here. So when we divide both sides by the square root of 3, we end up with a radical whose denominator we need to rationalize. When we multiply, we get 12 times the square root of 3 over the square root of 3 times 3. We get D equals 12 square roots of 3 over 3, or D is equal to 4 times the square root of 3. All right, doing our simplest radical form. Now that we know what D is, I can use it up here. F equals 4 times the square root of 3 times 2, which means that F is equal to 8 times the square root of 3. So making sure that we work through these exercises and examples is critical to the level of practice that we need. Obviously, some are easier than others, all right? So this is the easiest one because they give us the length of the short leg. Multiply by 2, multiply by the square root of 3. Here, we have to divide by 2 to find this, and then we have to multiply by the square root of 3 to find that. Over here, we have to divide by the square root of 3, rationalize, write in simplest radical form, and then double to get this one. All right, so these maybe are a little trickier, but it's work that we can do. Once we have this information, once we know the lengths of the legs, either on the 30, 60, 90 or the 45, 45, 90, then we can find the areas of those triangles using our triangle area formula. All right, and then here is an application item. All right, and this gets a little bit involved, and so forgive me on this one if this is a bit of a stretch of our power today, but we're going to do this. We've got this this quadrilateral, this awkward quadrilateral. It's not a kite, it's not a rhombus, it's not a trapezoid, but we do know that the length of side AD is congruent, the length of side AD is equal to the length of side CD, or that those sides are congruent to each other, which means that when I draw this diagonal, it makes, if I draw it correctly or well, it makes a 45, 45, 90 triangle. Now, how do I know it's going to be 45, 45, 90? Because this right triangle is isosceles, which means that this is 45, this has to be 30 because these add up to 75. This is 45, this has to be 60 because these add up to 105 using the angle addition postulate. So now the question is, if I know that this AC is equal to 20, then let me go ahead and try to find the area of this figure in simplest radical form. Essentially what I need to do is I need to find the lengths of these sides. I need to find the lengths of these sides. When I have these side lengths, I can find this triangle's area. When I find these side lengths, I can find that triangle's area. Then I can add the areas together. All right? So there's going to be a little bit of understanding some simplest radical form here, but really the point is to make sure that we can apply 45, 45, 90 triangles, 30, 60, 90 triangles. All right? So let's do that. So again, this is the harder situation for both cases because we're going to have to divide by the square root of 2 to find out what these legs are. We're going to have to divide by the square root of 3 to find out what this leg is. We're going to have to divide by 2 and then multiply by the square root of 3 to find out what this leg is. So let's tackle this one first because ABC is a little bit easier. So we're going to start with the hypotenuse is equal to the short leg times 2, which means that 20 is equal to the short leg AB, the length of segment AB times 2, or 10 is equal to the length of segment AB. So then the length of the long leg is equal to the short leg times the square root of 3. So side BC is the long leg. That's going to equal the short leg, 10, times the square root of 3. We've got that. And now these are, if they gave us units, the units are centimeters, the units are inches, we'd put that. When we don't have units, we don't need to write them. But I've got this one is 10, this one is 10 times the square root of 3. So let's then deal with our 45, 45, 90 triangle. Over here, we've got the length of the hypotenuse is equal to the length of the leg times the square root of 2, the square root of 2. And so I know that 20 is equal to either side, AD or DC, doesn't matter which one, times the square root of 2. I have to divide both sides by the square root of 2, which means that I'm going to be rationalizing my denominator, again, just like we did on that first slide of practice with the 45, 45, 90s. This gives us 20 times the square root of 2 over the square root of 4, which means that AD is equal to 20 times the square root of 2 over 2, or it is equal to 10 times the square root of 2. All right, which is actually both of these. It's also equal to DC. So here's 10 squared root of 2, here's 10 squared root of 2. So the question is, let's find the area. And the way that we're going to find that area is, again, by using our area formula from lesson 1. Let's go ahead and do that. The area on this triangle is 1/2 base times height. The base I'm going to call 10. The height I'm going to call 10 square roots of 3, which means that I get half of 10 is 5. 5 times 10 is 50 times the square root of 3. Square units. Over here, we've got 10 square root of 2 times 10 square root of 2 times 1/2. So 1/2 times base and height. Writing my formula out. The base is 10 square roots of 2. The height is 10 square roots of 2. When I multiply these, half of 10 is 5. 5 times 10 is 50. So that's 50 times the square root of 4, which is 50 times 2, which is 100. When I take these two and I add them together, here is what I get. The area is 100 plus 50 times the square root of 3. I cannot combine those and make that 150. It's 100 and it's 50 times the square root of 3. Those are not like terms, so I'm not allowed to add them together. And that is our total area in whatever those square units are. So that rounds out our work. And we should now understand and apply the properties for 45, 45, 90 and 30, 60, 90 triangles, those special right triangles, using the relationships that we have in this kind of formulaic approach to find the lengths of sides, use those lengths of sides to find the areas of triangles.